Hi guys, my new slides today seemed to not want to work, so I'm relying on the slides that I had last year. This was module 4 previously, now it's module 3, and I've just put a bit of clarification in here. So we're starting out on what is now module 3, an introduction to the finite element method, and I'm going to make it clear that we're looking at one key part of FE to help understand, we're going to use one half of really the two strands to the FE method, which is we're looking at the discretization part of it, and that's going to help us solve trusses really quickly. So that's what we're going over. This is going to be quick. I don't particularly like having slides because I never think that they're not very useful for when I actually want to give a lecture. So they're good for overviews, they're not good for mathematics or anything. So we finished module 2. Again, that was previously module 3, so I've got to keep changing this. This is going to get tiring, especially since this will change every time I bring anything else into this. So we finished that. I'm not going to change this again, but by now you should be sort of confident with how we solve statically indeterminate truss structures using the force method. Okay, so for that, remember, we're looking for two displacements, delta x and delta x. This one is how much a structure moves. With no redundant. So we take the redundant off, we see how much it moves, and then we set the redundant equal to -1 and see how much the structure moves in the other way. So then we get the redundant is simply equal delta x on delta x. And I've just done a recap of that, so you guys should be pretty happy with how to go through that, or at least by the time you're watching these lectures you will be. Homework, these slides haven't updated, that's very annoying. Homework's not to be announced, homework has been given out to you guys, okay? So you have received this, you've received your homework and it's there, you've got it, and I've received a couple of questions about it already. Some people have even completed it and shown me the solution. Superb, okay? Bear in mind that the homework for that module, again, let's just be clear, the homework, i.e. the one you've just received, so not TBA, I'm going to be asking you to solve it using the methods that we're going to be teaching. Okay, so we're going to be developing some methodologies that help us solve truss structures quickly using computational methods. Surprisingly, more of this module is actually taught on pen and paper than the previous module. So you guys could solve these by hand, but I'd rather you do it on a computer. Okay, so we're going to go through this, but bear in mind that a big chunk of your homework for this module is going to be the solution of things that we did in module 2. Okay, so I'm going to put a few different homeworks up for this module, some smaller ones, and camera just turned off. That's very weird. Let's see if I can get that to turn back on again. Goodness knows what's happened there. I've gone blue, that's cool. Okay, let me just mess around with the color balance. There we go. Okay, now I don't look like I'm super cold anymore. So where I was going with that is that bear in mind that the problems that we've done for module 2, I'm going to be setting as module 3 examples, and I'm going to give you some smaller homeworks along the way as well. So for module 2, I really wish my slides had transferred over. For module 2, is this frozen as well? Having a real good day with everything working here computationally. Let's unplug this. There we go. So in module 2, which is the one that we just did, we utilized a lot of computational methods. In the accompanying notes, there's some scripts written in MATLAB. I've sort of stopped using MATLAB in my personal life, or my professional life, and I switched over to Python. So I provided a mixture of codes written in the two. Now, the reason that we applied those, or I've tried to get you guys to do things computationally for Module 2, is that there were lots of calculations that we have to do over and over and over again. And you'll find this all the time when you're professional engineers. If you get to that stage, that there are often calculations that we have to repeat 4, 5, 600 times. And in that situation, we write scripts that help us do them multiple times over and over again. There we go, helped us save time within a single problem. Okay, so the codes that were written for Module 2, you'll notice that even though I was able to borrow bits of code from one problem to the other, normally things like helping me print out forces in internal members, the methods that we applied and the codes that I ended up writing, and the ones that you guys would have ended up writing, were bespoke for a single problem. We started out with a new piece of code with every problem. Had to write a custom method of joints, had to write a custom free body diagram. So the whole method, even though we weren't able to eliminate some of the boring bits using Python, using MATLAB, using Excel, whatever, they were still not generalized. And what do I mean by generalized? Well, a generalized solution would be one that we could chuck any truss problem at it. Okay, any similar problem. Now, trusses, remember that the truss frames that we're looking at comprise nodes connected by 2 force members. Okay, so I could have many of these in a problem. I'd have to have one there as well. Say this problem here could be solvable just as simply as this problem here, if we were able to somehow capture all the information about this truss, put it into some sort of spreadsheet, for example, or an input file, and give it to a piece of software, give it to a piece of code that we've written, and it would be able to produce the answer. That would be a generalized solution. Okay, it's very much not what we've done for Module 2. For Module 2, we took a look at this, we did a free body diagram, did a method of joints, we wrote code for those bits, and we're able to do those bits over and over and again quickly, but it wasn't this generalized solution. And that's what we're going to be trying to look at in this module. So the methodologies that we're actually using are the basis of a good half of pretty much what the finite element method is. You'll often see what we're doing described as the finite element method, and this is an application of the finite element method, but for commercial FE codes they're a lot more complicated in how they work. So what is FE? What is the finite element method? And it is what we say here. It's a broad description for a range of computational techniques that we use to do lots of different things that enable us to determine stress strain, displacements, amongst other things. Now the way that FE codes work in general, and we'll be going through this in the theory later, or in the first proper lecture of this course, but in general we've got some form of partial differential equation, and we're looking to see the solution of that equation over some domain. Okay, so the first step is then recognizing the governing equation, normally putting it into some sort of integral form that makes it a little bit easier to solve. We're not going to be looking at that too much in this course. What we're going to look at is the next step, which is discretization. And it's the God, I can't even say the word. It's that bit that is going to, I really want you guys to sort of understand as a powerful methodology that helps us solve things. We spoke about this before. If we imagine if we have a large aircraft wing, that's long, and I've sort of just drawn 3 sections there. I didn't necessarily mean to. If we have a large aircraft wing that's shape changes heavily as we go along, we could take slices through this wing and then extract information about each of these 2-dimensional sections. You guys would now be able to say determine where the shear center is for this section using a little bit of work that we would have worked out from, using a bit of an extension of that work that we did to determine the shear center, you also would have been able to determine the shear modulus, and then couple that with the polar moment of area, you'd be able to determine the torsional stiffness of these different structures. In conjunction with the Young's modulus and the area, we would be able to then replace each of these sections with a beam. I don't mean physically, we're not going to replace these with a beam. What I mean by this is that we could then determine the entire bending property of this wing, the bending behavior, by modeling it as a set of beams joined together. Because as long as this beam element here has the same bending stiffness as this section of wing, same torsional stiffness as this section of wing, and the same mass properties, then that's going to enable us to look at how the whole wing bends. Now, in order to do this, then what we've done is we've broken the wing up into finite elements. Okay, we've taken it into sections where we can describe the property and how that, so we can describe the property of beams, for example, because beams are governed by Euler-Bernoulli beam bending theory. So we would have been able to break this wing up into little chunks, and that side of things is what we call discretization. Discretization, that's the word, discretization. Okay, so hopefully, we're actually not really going to be able to look at a proper wing problem in this course just because it's too complicated for an undergraduate course. But what we're going to be looking at is how we can take, for example, one of these truss structures. So if we have a truss structure like this, we say, okay, well, we know how each member works. Each member's properties governed by its constitutive relationship, which tells us how much it extends when we apply a certain force. So since we know how this whole structure connects together as well, we could then determine a set of equations that gives us the entire relationship of this truss structure if we apply forces. And that's what we're going to be doing. So in solid mechanics, this methodology is applied on a large scale. We've got lots of different finite element packages, so you might recognize some of these names. And this is just to look at the stresses using finite elements on a wing flap. For example, here, you can see these individual cells that are occurring here. These are finite elements within this structure. So they've said, basically what we're saying is, we know how these elements sort of relate to each other and how in this methodology, how the governing equations would propagate from one cell to the next. And as a consequence, we can look at the global behavior of this aircraft flap. So we're going to be looking at the very basis of how we take something that we understand and then combine them together into producing some global property. We're not going to use any FE software though. We're not going to use Abacus, Nastran, any of those. Instead, you're going to be writing your own FE codes. Okay, and I know that's going to be making some of you more upset than you'd like to be because of your, you probably love Python too much, but I'm not going to mandate where you do this coding. Do it in MATLAB, do it in Python, do it in Java, do it in whatever. I don't care. Okay, and I'll be going through the theory of how we construct software. How we construct what's called the global stiffness matrix, and then I'm going to leave it up to you guys how this is actually applied. Okay, so what we're going through, fundamentally, we're saying how do we take some local behavior, which is a two force elements, and how do we construct it into a global stiffness, which is then, we've got an element that's rotated. And then how do we put it into this big thing called a global stiffness matrix, which describes the behavior of an entire truss. Okay, so fundamentally, the problem that we're looking at is, for our purposes, we're looking at truss structures. We're looking at truss frames because that's what we started out looking at in Module 2, and it's a really good way to describe how the discretization part of the finite element problem can be easily solved. So our problem is we would like to be able to describe a truss structure as a series of nodes, their locations, and a series of members, which is just how nodes connect to each other. You'll see that I've described that slightly differently. Node locations, for example, we would say got nodes and X and Y. So my first node would be the origin, second node 0, 1, third node 1, 1, and so on. I could describe these as a table. Okay, that's just saying where my nodes exist on a Cartesian reference frame. Connectivity, this says which elements connect which node to which node, for example. Okay, so I would say element 1 connects node 1 to node 2, and that's all the information we need to be able to describe what a truss structure actually looks like. So we'd like to be able to describe a truss by 2 tables, one of which is the locations and one of which is the connectivity. Okay, 2 tables will describe the entire truss. And then from those 2 tables, we want to be able to develop a set of equations that help us determine how do those nodes move when we apply forces anywhere on the structure. I have to answer this phone call, excuse me. Okay, so we would like to be able to develop a set of equations automatically from this that then enables us to determine the displacement of all of the nodes and the reactions on the structure as a function of the applied forces. Okay, so we'd like to automate the generation and solution of equations to solve all node movement and reactions as a function of applied forces. So the generation side of things, this is going to be forming the global stiffness matrix. And what that's going to be, the global stiffness matrix, and this won't mean much yet, but we'll get there. This is a big matrix, which we give the symbol K, and it is a square matrix n by n, or let's say m by m, where m is the number of nodes. Sorry, I should say n really, because m is members, so we'll say n. Okay, and so once we form the global stiffness matrix, this then enables us to set the problem up as KQ is equal to P. Q is a vector of nodal displacements. And P is just a vector of applied forces. And so we're going to set this problem up, and we're going to say this is the governing equations of our entire truss problem. And then we'll find that we can't solve it because this matrix is going to be symmetric, and then we'll find that we can't solve it because we can't invert it. So the way that we get around that is we then say, okay, we're going to solve this by employing some boundary conditions. And the boundary conditions are given by the fact that our structure normally is built in, for example. And then we're going to look at the difference between what are called homogeneous and non-homogeneous boundary conditions. We'll get there, and I'm not going to even bother writing that down, but we will get to that point in these lectures. Okay, so that's the problem that we're going to be producing. We want to start with this table that just describes how a truss looks, basically, and how it's connected. So we've got information about nodes, and then we've got information about how the members connect things together. We're then going to be able to set it up into something called this global problem. Global stiffness matrix multiplied by the vector of displacements is equal to a vector of forces. That's what we want to solve, and in order to do that, we need to work out how we can constrain our problem via the use of boundary conditions. Okay, so where we're moving on to with this, I'm going to move on to, these slides are awful, I'm sorry guys. We're going to move on to, in the next lecture, we're going to start looking at how we can describe spring elements in isolation. Okay, what do I mean by spring element? Well, I mean fundamentally it's a spring, which is exactly what we've dealt with sort of in real simple. Let me just move my stuff around on the screen. We've dealt with springs in really simple sort of statics before. So if we have a spring that looks like this, it's going to have some sort of stiffness K, and we can have forces applied to the structure. Let me just check I'm getting my nomenclature the same as I've done this before. Yep. Then I can apply two forces, F2 and F1 on this structure, for example, and then I would have two displacements here. So I could move node 1 and node 2 could move. And we're going to be able to set this up in matrix form. We will show, and I'm not expecting you to fully intuit this at this moment, but we could describe this as a nice symmetric matrix we're going to set this problem up like this. Okay, that's what we're going to be doing next lecture, understanding this and understanding how we can produce that, and we're then going to start joining springs together. Okay, joining springs together, putting them at different orientations, working out how that affects the whole problem. And we can see that for this one we've got two nodes, we've got a 2 by 2 stiffness matrix. If I put a third node on here, we'd have a 3 by 3 with the two springs joined together. So we're going to look at that in matrix form, how we put things together. And then we're going to realize that if we want to start looking at things in trusses, we haven't got springs, but then we've got K is simply the stiffness of our structure. So the stiffness of a truss frame member is simply going to be a function of its length, Young's modulus, cross-section area. We already know how to determine the stiffness of two force members. Okay, so we're going to take these springs, join them together in a single axis and form this idea of the global stiffness matrix, and we're then going to be able to solve this. And then we're going to change these to bars, and bars, like I said, it's just a case of taking that K and turning it into the relationship between length cross-sectional area, Young's modulus to determine the stiffness. And we're then going to start moving them all around at different orientations. And once we've got to that point, we've then produced a methodology that enables us to solve pin-jointed trusses. And once we've got to this point, this is only about week and a half as lectures, you should be able to solve all of the problems that we did in Module 2 using this methodology. Okay, and like I say, the fundamental theory here is extendable to complex shapes, 3 dimensions, using other sorts of members. So we could introduce beam members. Beams are able to bend in addition to extending. It's instead of being a 2x2 stiffness matrix for a single beam element, so for a single spring element, it would be a 4x4 because each node is then able to move both in terms of extension and vertically. And we'll cover all of this, and this will all start to make more sense as we go through things. So this is what this module is going to be. It's an introduction to this methodology. Okay, I'm going to try and break things down into one theory, one coding lecture, one theory, one coding, one theory, one coding, because all of the methodologies that we do in this module can be solved using hand calculations, but they'll just take a very, very, very long time. You have to get good at Gaussian elimination with matrices, and I hate doing that. So we're not really going to do any solution by hand, but I will show you how we construct things by hand, and then we'll move over. I'll be doing my examples in Python. I'll see if there's any other languages that I fancy throwing in just to show you guys that we can do this in other languages. If there are any questions, then you guys know where to find me. I presume you're all watching this lecture long after you've given up on your Module 2 homework. If not, then drop me questions as you get them, and I will see you in the review tomorrow. Take care, guys.